Right, so in this problem, we have this case. So the rate of change of y is proportional to y itself, where tau is generally a positive constant. And even though this process tends to run away, we want to implement control, which will have the result that we'll achieve a set point of y equals 3. And we'll first look at the process without exerting any control. In other words, when u equals 0. So we can simulate it just to see, but we can start out just saying, well, the general solution to this equation when u equals 0, the general solution to this part at least looks like this. So we can just see that this is going to exponentially run away from us. So let's see that. So here we've specified an initial condition of 2 just arbitrarily. We want to achieve a set point of 3. We are choosing a tau value of 5. At the moment, we don't need this Kp value because we aren't exerting control yet. And then here's our differential equation. We don't need any of these things because we aren't exerting control yet. So we are saying u equals 0, dy dt is tau times y. And so that's our differential equation defined. So that's your syntax for ODE int, right? If you want to use Python to simulate ODEs, you use the SciPy library. So you import SciPy, and then there's an integrate, and specifically ODE integrate that's in SciPy. So you provide the function. So f is the callback function where you've defined your differential equation. And you also specify the initial condition. So y naught is our initial condition. And we specify the times over which we want the solution. So here we are choosing to look at just between 0 and 5 using 500.
Awesome.
Yeah.
Some students are in the waiting room.
Oh, thanks. Where is my... Okay, thanks. They're joining now. Okay. So here, so that's basically our differential equation. And of course, we need to run this block first, make sure all the libraries are loaded. So, and I just use Shift Enter to run a block and go to the next one. So that one's run, and then I run this one again. And you can see here, it's running away, right? Clearly, I've limited us to t equals 5 because just slightly beyond t equals 5, it goes off to beyond our ability to retain the numbers. So that's definitely unstable, an unstable process. It's running away there. So now let's implement control. So we don't want u to be 0 anymore. Now we want u equals kp times ysp minus y. And in Python, your indentation does matter. So here we are adding control now. And we are doing that in the standard way. So the set point value minus the current value. And remember, in this function, you will always be, you'll always get the current value for y. Maybe just to check there, a few more people coming. So just to check there, is everyone familiar with SciPy's ODE integrator? How many, hands up, how many have used SciPy's ODE integrator? Okay, I'm not seeing any hands there, but maybe then just to mention, if you look at what it's doing, so if we print y here and run this, you can see all the values of y that it's going through over there. And we did talk a bit about this in class. We said, if you have an ODE and you want to integrate it, then you would basically take an initial condition, like in our case, we are starting with a 2 here. Then you stick that value of 2 into your ODE. So we know initially our y value is 2. We know our set point is 3. So on balance, this is a 1. And then, so that defines a value for u. And then this is 3, and sorry, this is 2. The initial value is 2. Tau is 5, so that's a 10. So dy dt is a specific number. I'm saying all these as numbers to emphasize dy dt is a specific number. So we do have a gradient dy dt initially, and then you can step up along that gradient, and that gives you a new point here. Now you've got a new value for y. You do the same process here. You stick in that value of y, recalculate all these things. That will give you a new dy dt. And then that's going to give, so that's a new gradient here. Then we step up to that point here. And you can see the integrator doing all that. It starts out with a value of 2. It's taken a very small step forward in time. It's not jumping forward by a value of 1 or something. It's stepping forward slowly, and you can see the value increasing there. So that's how our integration is working. Right now, I'm just going to suppress that. Is everyone clear on that? That's how the ODE integration works. Okay, so we are integrating forward in time, and now we are doing it with a controller. And I'm just going to drop the KP value first. So if we set KP equals 0, again, we are not, there's no control, right? Basically, KP equals 0 means U equals 0. So we get the same result, it runs away. Now let's start adding in some control. Let's try a value of 1. And now you can see it's still running away, but not as fast. Before it ran away to a 1E11. Now we are at 1E9, so that's a bit better. Let's try a value of 3. And now you can see it's even better. It's still running away, but it's at 140,000 instead. And now let's try a bigger value. Let's try 30. And now you see we do start at 2, and we are reaching a steady state. It's not quite the steady state we want. We wanted a value of 3, but that's what we get for this KP value. So there comes a point where we transition from being unstable. So at a value of 10, it still works. Let's try and find the value where it's just crossing over. If we try a 7, 7 is giving us steady behavior. Not giving us, so the 4 doesn't work. 5. So yeah, it looks like 5 is the critical value. So at a value of 5, it is still increasing. It will go off to infinity like this, but you can see it's not exponential. It's not exponentially increasing. It's not exponentially decaying. It's rising linearly. So that implies to us that that is a that's a critical point. And if I increase just slightly here, let's say 5.01, and let's say I increase the time. Okay, let's just use a bigger value, 5.1. So you can see a slight kink. Now it's starting to curve this way. It's not curving the other way, going up like that now. Now it looks like it's slightly curving this way. So let's increase the value further. And you can definitely see the curve now. So if we increase this, then you can see we are getting to stable operation. And again, we aren't yet getting to the steady state we want. We aren't getting to a 3. We are getting some other steady state. So at least it's stable now. And as we increase this value further, let's try even 70. Then you can see even at this fairly strong control action, we are not on 3 yet. We are somewhere higher than 3.2, but it is pretty close to our desired value. And you see, as you increase this, let's try even 7,000. It is giving us what looks like is on 3, but if you look at the actual value, so if we just print y again, and you can see it's never quite getting onto 3. And that's because this process is inherently unstable. The process is constantly trying to run away. And in proportional control, we only take action when there is a difference. So the process tries to run away. The moment it goes a bit above the set point, we start applying this flow rate. And by the way, this is an exit flow because this number is going to be negative. So your set point is 3. Your actual value is slightly more than 3. So this is a negative number. So this is something like an exit flow. So the process itself is tending to give us more and more of that y value. And our control action is to try to pass that out of the process. So that's, if you like, a crude form of control. We can just simulate the ODEs and play around with the values. So the KP value or the tau I value. So yeah. And so you can change your process type here, and you can change your, so you can use the integral as well. You'll need to write in some numerical integration also, which you can do. And then you can see whether it achieves your control objective. Okay, any questions or comments on that? Okay, so if you like, this is, Siyabonga, you've unmuted. Okay, no questions or comments. Okay, so you can play around with this. This is the crude form of control, if you like. This is sticking in the time domain and just applying control directly. So I guess I put forward this example just to remind ourselves we can always do this. It's not like, we always have to go into this S domain. And yeah, this one is pretty much the same thing. Okay, but now let's go to our kind of professional way of doing this. And like we said last time, our time constant, that we can figure out the point of instability by examining our time constants. And what we had also learned is that the poles of G are so poles of G closed loop is the time constant lambda. So we just need to find the poles of our closed loop, so the values of S that make a G closed loop go off to infinity. And we can see that this is, which are the zeros of 1 plus G open loop. Okay. So all we need to do is find the S values where we get 1 plus G open loop equals 0. So what are the S values where we get this? And so, as I say, I've written this code, which is just a kind of simulator, and you've got a bunch of equations that you can apply here. So all these are G open loop, right? When I say GP, that's the process itself. So G open loop. And so we can choose any of these equations. So just uncomment the one you want to simulate. And then you can see the equation here is, this is the thing we want to get the zeros for. So we create this string. We say 1 plus KP times the process, right? So we know for a proportional controller, that's going to be the denominator. So we want to know what are the zeros of this equation. And to find it, I'm using the symbolic solver. So in Python, it does have a symbolic solver, right? So SymPy, you can use that to do symbolic solving of equations. And so we are using a symbolic solver to work out the equations for when this thing equals 0. And let's just run this one. And never mind the solutions just yet, but you can see here that it's actually giving us the equations here. So that's the original equation. And if you look up here, let's see, no, that hasn't run yet. Okay, so here, if you look at it, our here's the function we chose, 1 over s plus 5. We've created this string 1 plus kp times 1 over s plus 5. So you can see that here. So that's defined the equation for which we want the zeros. And then we are using the symbolic solver to find all the solutions to this. And it's printing the solution. And in this case, there are just two solutions, minus kp and minus 5. Or I mean, minus kp minus 5, just one solution there. So the real part of the solution, it's all real. This is all real. So minus kp minus 5. That's the only solution that we have for this simple situation, 1 over s plus 5. And then what's plotted here is the solution. So this blue line, that's the one root that we have. And so for different values of kp, it's generating the values of s. So these are the values of s that satisfy that equation. And so looking at these values, we can see none of them are positive numbers. So we can say this process is stable. So we can look at it in this way. The other way to look at it is to let kp vary, right? The problem with this graph is we can't really see what value of kp we have at each stage. We are only seeing the imaginary part and the real part of the root. What's a little bit confusing on this drawing here is that we have these two other lines, those 45-degree lines. Those are not roots or not solutions. I'm just drawing 45-degree lines because we'll see later those help us actually optimize our values for kp. So for now, just ignore these 45-degree lines. So just carefully look at this figure, see where's the 45-degree line, and just ignore that for now. The only root we have is this one, minus kp minus 5. Any questions or comments there so far? Okay, so this blue line is the thing of interest to us, but looking at just this blue line, we can't see the values of kp. So we plot here as a function of kp the root. So this root, it has two parts, the real part and the imaginary part, right? So if you look here, all these values of the root of all these values are s values. And so they have a real part, and the real part is has all these negative numbers, and the imaginary part is always 0 here. So if we want to see how s is changing with kp, we need to consider two things. We need to look at the real part, and we can see the real part is going through all these negative numbers. And we need to look at the imaginary part. And the imaginary part, you can see the green crosses here. Those are all 0. So there's no imaginary part. In other words, there's no oscillation in our solution. And we only have negative real numbers. So it's stable and not oscillating. And in fact, this problem, if you translate this first problem into the Laplace domain, you'll see that this is the same as this case, right? I'm not sure. Let's see. E to the plus. So, well, here's the other case here, s minus 5. So if we plot this one, then we can see that, let's see, did that run s minus 5? Yeah. So you can see the solution for this case as well. So this, this corresponds to our first problem, and it does correspond to what we found, which is that there are values of kp for which we get stable operation. So in this case here, where it's s minus 5, that is more like the problem that we had initially. So if you look at our original problem, your value of tau here, that was a plus 5. And if you think about your Laplace transformation, that's the same as s minus 5, 1 over s minus 5. So if you run 1 over s minus 5, then those are the roots of interest to us. So if we run that, you can see here, there's a bit where it's going past the 0 point. So we saw it took a value of about 3. Let's in fact limit down how far we look in KP here. So we found quite early on that we went so it was around a value of 5. So across a value of 5, we got stable control. So if we run this now, you can see it more clearly here. So when we have values that are, you can see here, for a KP value past 5, that's the point where we get negative real numbers, right? Before 5, the real part is positive. That means it's unstable, like we showed earlier. And then after a value of 5, when KP is more than 5, then the real part is negative, and then we get this, and then we get stable operation. It does steady out. So it doesn't guarantee we'll get to our set point yet, but it does guarantee stable operation. So that's how you read the graphs. And I acknowledge it's a little bit, back and forth because we are juggling so many dimensions. We need to look at different graphs to form the complete picture. So that's the other thing to do here, right? Do this enough that you have experience with juggling the different figures to figure out, okay, what's going on in this region, what's going on in that region, where's my KP value? So that's what we are always trying to get to. What are the controller values that give me stable operation? And then later on, we'll look at what are the values that give me good operation. So it must be stable and get me to the set point quickly. Any questions or comments there so far? Okay, so let's look at a couple other ones. So this was a simple unstable case. If we look at the second order case, and just run that. So in that second order case now, we do have two asymptotes. Yes. Hi, sorry, is there a question?
Yes.
Hello.
May I please ask about the orange lines, the 45-degree orange line?
So are you asking what's this orange line?
Sorry.
Sorry. Yes.
Oh, may I please ask about the orange lines, the 45-degree orange lines? Do they give us the region where we'll have optimal KPUs?
I'm just reloading that earlier example. Yeah, so these orange lines, I haven't actually said what they are for yet. But yeah, that is what will help us determine good values for control. So most of the time we'll be looking for where does my route intersect with these orange lines. And as it turns out, as we'll see later, that does give us good control. But for the time being, you can just ignore those. I wonder whether I shouldn't switch them off. Let's. Do you have another question around that?
No.
Okay, thanks. And I'm just checking the chat here. It's fine. Okay, so that's that was the first case. Now let's look at another one. So let's say 1 over s plus 1 and s plus 2. So this equation looks like this. So in the second one, G open loop equals 1 over S plus 1 S plus 2. So it's a second order process in open loop. And so like before, we will multiply by Kp and look for the roots of this equation. So let's just run this. And we can see here, yes, that's our equation. And here we've got the two roots. So the symbolic solver has given us the two roots. And then it will, then we'll take these strings and evaluate these strings for different values of Kp. And those will give us different S curves. And so now we have two roots. So the 45-degree line that has changed its color now, just because I'm always plotting that last. So, so the color changes. So now the first two curves are the roots. And we can see in the S-plane that these are always on the left-hand plane. So they are always negative in the real, in terms of the real part. So that tells us it's always stable. Well, we should just check by increasing the Kp value, and let's see that we are not straying into regions where it does go positive. And we can see it's not going positive. So that looks fine. So it is always stable. It does start oscillating. So there are cases where we have significant imaginary parts, and so it does start oscillating. And then if we look at how the roots look as we change Kp, then we can see in the first roots case, the real part, right? The blue line is the real part. The real part is always negative. And then we do get imaginary parts here. Excuse me. And then we have to do this for each root, right? So before we only had one root, so we were talking about one plot. Now we've got a second root, so we need another diagram for that. And you can see here, the real part is still negative, so it's still stable, and we get oscillations. So yeah, that's what we expect in this case. And so if you can find the equivalent time domain for this, and I think I might have it, so try and find that. There is a second order one here, I think. No, that's not it. Yeah, so here's one with a tank step, but this was just the first order case. Here's one, here's a second order case. And yeah, here you can see the oscillations. And as you change these values, you'll get some cases where it oscillates and you do get to a divergent case. Here you can see the B value. There is a value for B where you do get a stable orbit, but then you cross over to instability where your response is growing. And then inside of that, you do get to stable operation where it does go down to a single steady state. Then a more chemical engineering type problem is here. So this is a second order case, tanks in series. So this is our transfer function. And if we run this one, then here you can see that oscillation. So here we can change our inlet flow rate and then our control constants. So K1 and K2, well, that just relates to the extent of the space-time. But you can see that oscillation. You do get an oscillation. In this case, it's stable, and yeah. So the same features that we are looking for. If you find the equivalent, how can I say? If you find the equivalent second order process, you'll see those oscillations there. And that's what we detect here. So simply by looking at these graphs, we can tell, yes, there'll be oscillations. The imaginary parts are not zero, but the real part is negative. So 0 is here. You can see the real part is below that. And you can also see that here, the real parts of these two roots are always in the left-hand plane. Okay, so that's the second order case. And then we can also look at this case where we have the second order in the denominator, but you also have in the numerator a term that also looks like tau s plus something. So if we run this one, and we can see that there are, yeah, I'm surprised, I think. Yeah, so we've got our all our roots look to be negative. The real parts are negative, and you can get oscillations. So again, that's something you can say there. So those are, so this is the simulator. You can pretty much put whatever equation you want in there. And if the symbolic solver can find the roots from that equation, then it will help you visualize all of that. So we want to be able to do this in or from the using the principles that we established also. So we had said we have these 5 principles. And so we look for the, we look at when Kc equals 0, what are the values of S? When Kc goes off to infinity, what are the other values of S? We also use the fact that the number of roots, of root loci, that equals the number of poles. So n, if n is the number of poles, then that's the number of loci we'll get. Yeah, we said complex conjugates, and that there is a center of gravity for all our loci. So we're out of time, unfortunately. So let's just look at this. Yeah, there's an example where this is worked out. So there is a worked example in the set of notes. So here we have this process. So these are all in series. So overall, our open loop process looks like this. And then we are implementing proportional control. So it's Kc times this. And so if we are implementing PI control, then our controller has that function. So if you look in the notes, we do derive for a PI controller what the transformation looks like. So we have to multiply the controller by the process transfer function. And so it looks like this, right? So Kc times S plus 1 divided by S, so that 1 over S comes from the controller, and then the process itself contributes this part. So here we have 4 poles, right? 0 is 1 pole, -2, -3, -4. So we have 4 poles here. And then we have an S plus 1 in the numerator. So 4 minus 1 is 3. So we have 3 loci. And so there are 3 roots that we have to pursue. And then we can look at what values of Kc. Well, for that, we need to multiply this out and do 1 plus that. So for a value of Kc equals 0, then we can show that those are the starting values. And then our center of gravity for all these asymptotes we get from that formula. So according to that formula, we take the sum of the poles minus the sum of the zeros and divided by the number of poles minus the number of zeros. So that's what we are doing here. So the sum of the poles, if you add all these poles together, -2, -3, -4, and then the zeros here, here, let's see. Let's just see. This is purely in terms of I need to check this. I would imagine that it's -1 as well here. And then number of, so it depends whether we're talking about the process only. So if I look at this, this looks like the process only, whereas I think it should be done on the process plus controller. But let's just take for now that we are only plotting this one. Let's say we are not yet plotting the controller. We want to add the controller separately. So doing just the process, then this makes sense. And then, so that's the center of gravity -3. You could also end up with an imaginary number here, but most of the time these are real numbers. So that tells us we have a -3. So let's just sketch it. So on our line, we've got a -3. So our center of gravity, you can say, is sitting here on -3, -3. And then, and then we can calculate the angles that all those asymptotes extend towards through this formula. And you'll see in the notes, we justify where this formula comes from. But basically, we choose values of k that run from 0 to the number of asymptotes -1. So it goes 0, 1, 2. And we use this formula here. So when k is 0, then this is 1 over, and that's we've taken as a 3. So it's 1 over 3 pi. So pi over 3, that's our first angle. Then when k equals 1, it's 2 plus 1, which is 3. 3 over 3 is 1, so that's a pi. So the second angle is a pi, and then the last one is 5/3 pi. So pi over 3, remember pi is 180 degrees, and so this is 60 degrees. So it looks like our first line is approximately like this. So the first asymptote, and our center of gravity is here. So our first asymptote will eventually end up moving along that line. Then the next asymptote is on pi. So that's the next one. And then the last one is on 5/3 pi, which is the complex conjugate of the upper one. So that's the other asymptote. And then if you take the actual, initial values, then you'll find you'll be able to effectively show how they curl into these different transitions. But that's how we can get the asymptotes. So from this alone, we can say, well, on this route, we don't get any instability. Along this route, there is a point where we do enter the positive right-hand plane. So it does look like we will become unstable for certain values of k. So we need to find these points. Right? So these so-called breakout points, there are ways to calculate these, which we'll look at. Right? But that's just quickly how we can draw these asymptotes. So number one, and again, apologies, but it looks like we didn't include the controller. We just did the process for now. So just looking at the process, we only have poles here. And so we have 3 poles, and we can say that the 3 poles are -2, -3, -4. And so we can work out the center of gravity using this formula. And then we can work out the angles here. And then that tells us everything there is to know about the routes. So yes, we can do it numerically like we showed in the simulator, but we also have available this method for drawing our asymptotes. And you can see in this way, we can very quickly tell whether or not this is a stable process. So we can say, yes, there are regions where it can be unstable. And so it's important for us to figure out where these points are, what values of Kc will get us to here. Okay, any questions or comments there? Okay, so using that approach, take the same in this tutorial. So in this tutorial, there are all these case studies to look at. So number one, you can run them through the simulator, and number two, you can use that asymptotes method to draw them and see that they agree. So do the asymptotes, calculate the center of gravity, calculate the angles, draw out the asymptotes, and then use the simulator to also run these and see if you get agreement between the two. Okay, so that's your tutorial there. Any questions or comments on that? Okay, if not, then we are over time for today. Thanks and see you in the next one.